Hello everybody and welcome to our next Calculus Level 1 video, which is going to be about related rates today. And what is a related rate? Well, let's go down here and we'll begin talking about this because I've laid out some 3 questions that we normally would use to look at something to sort of understand what we're talking about. We need to know when we're looking at a related rate, what makes it a related rate, and how we can deal with a related rate. And the real kicker to knowing what a related rate is the key of remembering that a rate of change is a derivative. A derivative is not just something that we can use to obtain the slope of a tangent line of a function. We can also use it in a more realistic real world way. And it's actually the way that it's used a lot in terms of physical sciences and statistics or something. If it needs to be used in those situations, they can determine a rate of change in those two things. Like the easiest thing to think about, right, is um, if we were looking at a change in velocity over time. This is bringing in a little bit of physics, but it's going to illustrate what I'm talking about very well. So what if we were looking at a change in velocity with respect to time, right? This is the same thing if we were to look at this algebraically as delta v delta t. And that's something that this is is something right here that people are very familiar with, right? If you've taken any algebra class or in a high school level physics course even, you've probably seen delta v delta t or delta r delta t, just any really changing variable that's going to be changing with respect to time is that. And really that's just a simplified is a good way to put it, is a simplified version of a derivative because a derivative is differential. It can be taken multiple times, but this is sort of just a way to illustrate these two things changing affect each other. So what's a real world example that we could look at whenever we're trying to define maybe when we're looking at a related rate? Well, the way I had it explained to me that I always found very useful is, let's say that we had a balloon, okay? We have a balloon, we'll make it a red balloon. That is a bad balloon. Okay, we've got our balloon, and our balloon is being filled with air, okay? What changes when a balloon is being filled with air? What changes when this is happening to the balloon? Well, the thing most people would probably think of is if that balloon is maybe just now not filled with any air, it's not filled with really any air. It's kind of just flippity floppity, not doing anything, but it gets pumped full of air. That balloon gets a pretty big shape. It gets a larger radius, right? We can see that the radius of this is going to be smaller here, whereas if it's going to be bigger here because it's got more air, more volume, a higher density inside of it. Well, we can relate these two rates if we were to try and assign numbers to how much volume is being changed in the balloon with air at a certain point, with wanting to find what the radius is at that exact time. So the easiest way that we can think about this is let's look at this in we're going to set down some ground rules for this problem. We're going to say that it's a spherical balloon. You know, not your average balloon. It's just that way we can make this increasing uniformly, the volume being uniformly increasing across the entire area of this balloon instead of just having it sort of, increasing at the top, not so much at the bottom. It's just going to be a sphere, and it's going to make it a lot easier on us while we learn this. And let's just say that its volume is increasing at a rate of, let's assign that a number of 100, multiples of 10, very easy to work with. Centimeters cubed, because we're dealing with volume, per second, because it's changing with time, and we're just going to keep that in our SI unit of seconds. And we want to know, what do we want to know? We want to know how fast drew an extra E on accident, how fast the radius of the balloon is increasing oh, sorry, not is, how fast the radius of the balloon, wait, yeah, is increasing when the diameter is 50 centimeters. All right, so we have an essential problem sort of laid out in front of us, right? We know the shape of the thing we're dealing with. We know we're going to have to use the formula for volume of sphere at some point. Otherwise, it wouldn't give us that information. We know that the volume is increasing at a rate of 100 centimeters cubed per second. And we want to know how fast the radius of the balloon is increasing when the diameter is 50 centimeters. So we kind of get a time marker with this 50 centimeters right here. We sort of get a time that we're going to be looking for. And so we can break this down, right? Like I had just done, but with a little bit more clear notation. So let's write down our given info. Our given info is that volume is increasing at a rate of 100 centimeters cubed per second. And our unknown is the rate of increase of the radius when the diameter is 50 centimeters. So we have very clearly in front of us a thing we have and a thing we're trying to look for. And from there, we can kind of figure out, with logic, what we're supposed to do next. So what would be the next logical step? Well, the next logical step would be if we're going to be working with these bits of volume and diameter and radius is to kind of get some general notation. So let's say for this problem, we will let V represent volume and R represent radius. And now let's think about what rewriting this is given us. And remember what I said at the beginning of this entire thing, is that the key to this is remembering that rates of change are derivatives. And so in this, we can tell that both of these are functions of time. The rate of increase of volume with respect to time is going to be, let's say, dv dt. And the rate of increase of the radius with respect to time is dr dt. Right? This is not anything crazy or anything out of our comfort zone. We know we've seen this several times with anything that we've done in the past with this so far. And knowing these two things, we can restate what we did up here with this given and unknown and rewrite that out in a mathematical way. So that way we can make it a little clearer to understand. Because that's the real thing that is hard about word problems is figuring out what the problem actually is and being able to assign numbers to it. So that's what we're going to do right here. And then our unknown dr dt when r equals 25 centimeters. Now, in order to connect these two, we need to relate v to r, right? The whole entire thing of this is related rates. And if we can't relate these 2 points together, then, well, we're at an impasse. So let's real quick find a way to do that. Well, what's the easiest way to do that? Well, we know we're working with a sphere, and we know we're working with volume and radius. Those two things are it should almost immediately jump out at you. Well, the formula for the volume of a sphere, is V equals 4/3 pi r cubed. Right? And so we have our two things being related right here. We have our V. Let's go ahead and underline. We have our V and we have our R. And we can assume that this is going to be relating to that shape because it is. It's the formula for that shape in specific. Now, in order to use this information that we have figured out, we need to determine what each side of this relationship is going to look like. So, let's do this. So, we can, with what we've been given, we can know that dv dt is equal to dv dr. dv dr, dr dt. Because if we were to think of this as quotients that were equivalent, which they are not, that is one of the most important things. It's easier to comprehend if we think of them like that, but it's important to keep this in the back of your mind that these are not quotients. This is not an actual equality that we can say, all right, this minus this is equal to this. That's not the case. This is merely operators working with notation and realizing what we've got here. All right, this is not an actual equivalent quotient. This is just to sort of visualize it. If we were to multiply these two things together, hypothetically, whatever our drs were would cancel each other out, and we'd be left with dv over dt. Is that clear? Because we do not, with everything that we already have to keep track of, need to add in something else crazy to the mix. All right? Now, we need to determine what dv dr is, so that way we can actually have an equivalent here. Because right now this is just notation. We want to get this to where we have an equivalency. Well, if we use the chain rule and we look at everything right here, we would end up with this. However, we can also relate dv dr as 4 pi r squared dr dt. This dr dt just kind of came over, and then this is represented with that. Now the question that I have for you is, are we clear? Are we clear why this is that? Well, okay, if we think of volume in relation to a sphere, and we were to take the derivative of this function, because that's really we can do. So if we were to say, all right, we want d dr of this v function, right? That's exactly exactly what that operator right there is saying. Well, what is dr of v equals 4 over 3 pi r cubed? Well, power rule this, guys. We just gotta power rule this. Multiply the 3 over. That cancels with that 3, and we decrease the exponent by 1 to get 2. So this becomes 4 pi r squared. And we just plug that right in here. Just connect those two things. Remember, this is the same thing as this. And then we have our drdt, so that way we're able to basically say, in a more simplified form, without all the lines and everything, dv dt is equal to 4 pi r squared dr dt. Alright guys, now what do we want to do for our next step? Well, we're right at the finish line. We are right at the finish line. All we need to do is think of this now, once again, think of this as an equivalency. We cannot treat the two operators as quotients because they are not quotients. They're operators. But the one thing that we have in this equation that is not a quotient or an operator is this 4 pi r squared, and we are looking for dr dt. So, well, all we have to do, 1 over 4 pi r squared dv dt equals dr dt. Does that make sense? All we did was divide the 4 pi r squared over. That was all we had to do. And this is the point when we get into our conceptual things, correct? Because we have the formula for our answer. We just need to now figure out how to obtain that answer from this formula by recognizing what the things in this formula are. Because in reality, what it's given us is very easy to work with here. We just need to remember what everything is. This, right there, that's the rate of change. Rate of change for radius. This is the rate. We'll call it ROC. The ROC of volume. And this is our input for R. So what do we do with that? Well, if this is the rate, and we already know that we have an ROC of volume and an input for R, well, let's find out what these values are. At the very beginning of this entire situation, we are explicitly told that the rate of change for volume is 100 centimeters cubed per second. And we're also told that the diameter equals 50 centimeters. Well, to find R, that's d over 2. So therefore, it's 25 centimeters. Well, let's plug this in. So we have 1 over 4 pi 25 squared times 100. And we get 1 over 25 pi equals dr dt. And now really, this is a very exact final answer to this right here. And if you wanted to get a sort of approximation, you're like, all right, that's all well and good, but what is 1 over 25 pi actually relating to with actual unit measurements? Well, if you were to put this into a calculator and determine that 1 over 25 pi is equivalent or approximately equal to 0.0127 centimeters per second. And that is our rate of change in the radius. So what all did we confer? What all did we confirm in this video? We confirmed that derivatives are rates of change. And in order to be able to relate these two rates, whenever it gives us one and asks for another, we can think with our heads what a real world situation where one of these things would be affecting the other, and a formula that includes both variables. And if you have those things, that's really all you need. And you can set the two to equal each other by using that chain rule that we mentioned up here, because there are two really main hard parts of this whole entire thing, and that is this step right here, recognizing what all this is, knowing that this dv/dr is the same thing as taking the derivative of the volume with respect to r, because we have our formula, and then down here, knowing what all this is asking for and what we actually have in front of us. Because if not, if you don't know what you're thinking of, if you don't know that dv dt is the rate of change of the volume that it gave us at the very beginning of the problem, you're going to conceptually hit a brick wall and you're going to be stuck and you're not going to know how to complete a problem. But that's okay, because the more you practice it, the more you'll get better with it, and the more you'll be able to make those connections, and it'll just get easier and easier and easier over time. And that's really the goal here, is to practice and to make sure that we really understand what we got, because if we do, you can use related rates for a lot of situations, like a whole lot of situations, not just for balloons, but if you wanted to find out necessarily, if you wanted to find out let's think of something right off the top of our head. Um, like if I wanted to say maybe we're pushing a ladder. We have a ladder up against a wall, right? We have a ladder up against a wall. If this thing is sliding down with a certain speed, we can find how much distance is being covered in this direction at a certain speed at a certain time t as well. So it's really neat. You can determine basically what's happening at two different points and be able to identify the individual things. And it's a really important skill to have whenever you get into derivations of important formulas, and being able to actually determine that, okay, well, maybe this formula would be more benefited if I related its rate to something else, or it can just really make your life easier depending on the application of it. But that concludes it for this video, and I hope you all enjoyed. Thank you for watching, and I'll see you all in the next one.